So this is the third part. I should be in hurry because it was too long. The first two parts were too long. But okay, one important thing about the matrix measure, we should know how to characterize the zero measure sets, yes? And this is the remark or theorem, maybe remark, not very difficult. The following conditions are equivalent. The first condition, oh, of course, here omega is measurable set, yes? So for measurable set and matrix measure, one condition is, the first condition is this has the matrix measure 0. The second condition is that the trace measure is 0. So we see that we have something more than only absolute continuity of this with respect to this, but we have also the opposite. This is equivalent. Yes, this is very important. This and this is equivalent. So just we can sometimes forget about the matrix measure and only remember about this scalar measure. And the third condition is like this. We can here take the trace measure or M measure. Now we know that this is the same of the set of those T in omega. I'm sorry. We take the set, this subset of those T from omega that for which the fixed fixed trace density is non-zero matrix, and this has the measure 0. Yes, we can say that almost everywhere in omega, in the sense of this is 0. Yes. Okay. Moreover, so this is after this equivalence. So those three conditions are joined. These are equivalent intrinsically, and moreover, the trace measure or M measure, this is the same, of those T from the whole capital omega, that dm of T is equal to 0, is 0. Yes? So, in some sense, if we want, we can change it like this, that this is an empty set. Yes? Just. Yes, because this is a very small set. So, it's almost everywhere non-zero matrix. Yes, this density. And this is quite easy to understand. Yes, because when we see this, it's almost obvious. Yes. Without this, we would not have the equivalence of this and this condition. Because we obtain this by integrating with respect to this the density. Yes. So it should be non-zero, or almost everywhere. When we know that the condition, the equivalence of this and this holds. So I will not prove this. This is not difficult to prove. This is quite easy. Okay. So, this is another condition. This is a condition for those omega which has zero measure, and this is the information about the whole omega. Yes. So there is no direct relations. Okay. So now we know quite a lot about the matrix measures, and we can start to construct the L2 space, our main space, which is a generalization of the usual L2 of a measure space. This is very important for us Hilbert space, which is based on matrix measures. And this is quite sophisticated. It's not trivial to define those spaces. And I can say that when you try to find this in the literature, you can find a lot of mistakes and false results. You should be very careful. I cannot recommend you a good bibliography. In some places there are some parts which are okay, in some not, and really false results you can find quite often. For instance, you will see at the end, I hope I will show you a convenient subspace of this space, and in some books and it will be really subspace. I will denote this by L2 sigma of M instead of L2 of M. We will construct this, and there is an important subspace of this, which is not a dense, which is a dense subset, but this is not the whole space. It is the Hilbert space. This is sometimes not. And many authors defines this using the definition of this, for instance. Because this is quite easy to define this without using the density, the trace measure, and so on. And to define this, it's quite delicate. But the general idea is similar to the definition of the usual L2 of the measure space when we first define the L calligraphic space. So this is the space of functions. Here it was the space of scalar functions, and when we change this for matrices, it will be the space of measurable vector CD vector functions, and it will be the space of classes of functions in some sense. And this sense will be not so trivial. It will be not the similar sense as it was for usual A2 spaces. That, for instance, we identified the functions which are equal on the set which are equal for almost all T from omega in the sense of matrix measure. No, this is not the same. So this is delicate. This is one thing, not only this one, but there are several delicate technical, we can say, problems, but it's important. Okay, so we should be careful here. Okay, so we shall start from this, and then we shall obtain this just by dividing. So we will construct something which we can call semi-scalar product space. Yes, so it will be the space, the linear space, with the scalar, something similar to scalar product, but it will be semi-scalar product because it will be degenerate. And then we will introduce, of course, the semi-norm, and then we will just divide in the sense of quotient space, but the subspace of those vectors, those functions, the space of those functions which will have the semi-norm equal to 0. And this is the standard construction of many spaces in Banach or Hilbert space theory. So, we start from the definition of something which I will denote in strange manner maybe. So, first we consider functions on omega which has the d-dimensional values. So these are not complex number now, but vectors of the dimension d is measurable. Measurable with respect to m. And we fix matrix measure. Matrix measure on m. Yes, d by d. And now, and we fix also the spectral density, not the spectral, the trace density, yes, for it, in this convenient manner, as I told, that we want that it is non-negative matrix measure. Yes. I need some chalk. Okay, so I define such a value with m here. I will define this like this. What we do? We will compute the integral over omega with respect trace measure. So we take n t, we consider such a function that here it will be the scalar product in CD, the usual scalar product, the Euclidean scalar product in CD. And here we take the matrix, the density matrix, dm at the point t, and we take this on f of t, and here we take also f of t. Yes? So for each t we consider such a form on f of t. So this is non-negative, so this is also non-negative. So this can be a number, and this is also measurable because this was measurable, the function was measurable, so it's easy to see that this is a measurable scalar function and non-negative. So we have only two possibilities. Yes, it can be finite or it can be plus infinity. So it belongs to 0 plus infinity, let's write, including plus infinity. And now the definition of L calligraphic is just like this. L calligraphic of M is just the set of all those F measurable No, like this, I will not write again this condition that this is vector valued f measurable such that this is not plus infinity. This is finite. Is real, or okay, is less than plus infinity. Okay, so this is just the set of functions, and now it's quite easy computation that it's not only the set of functions, but this is also a linear space. It's quite easy to compute that this is a linear space. And then we'll define the semi-norm and the semi-scalar product. Yes, and it's quite easy to guess how we'll do this. Okay, so we define the semi-norm. The semi-norm of f from, it will be everything now for f or f and g from L2 of m, and we define this just like a square root of this value. Next, we want to define the semi-norm, not semi-norm, semi-scalar product. And the definition is like this. So this is obvious that this is a number, yes, but here it's not so obvious that this is properly defined. We should prove something to know that it will be okay, but it's not very difficult. I'm sorry, I have not enough time to do this, but you will find everything in my manuscript. So so instead of taking here f and f, I have here f and g, just, yes? And it's not so difficult to prove that it has sense, that this is a function which is integrable. This is the integral function, and it's not very difficult to prove. Okay. So this is the definition. Mogliśmy let us write properly defined. Yes. Oh, it's just this is okay. To prove this is properly defined, you should first take the square root of this non-negative operator and to divide it, and then to use Schwarz inequality, I can say, to prove that this is okay. This is one, and okay, and the fact is that defining all those, I will get the semi-scalar product space. So what does it mean, semi-scalar product? Semi-scalar product, again, it's everything what is the definition of the scalar product, but not the non-degenerates, yes? So this is, it should be, what's the name? It should be sesquilinear, non-negative, conjugate symmetry, yes? These are all those properties. And this is linear. It's also easy to see that the space is linear. And of course, we also see that this, when you consider an element of this space, so this is just the same what the scalar product of f and f, the semi-scalar product of f and f. So this is similar notation, but this is one argument and these are two arguments. So. No, this is the same. But 1/2 is here. 1/2 is here. Look, when I define this, yes, it's, this is, I obtain this when I, instead of G, I take the same F, yes? But when I want to get, yes, when I want to get the semi-norm, I should take the power half, yes? Okay, now we should consider L2 0 of M. We define this is the so-called zero layer. The zero layer, this is a subset of those functions f from L2 of M for which the norm, the semi-norm f of M is equal to 0, yes? This is the zero layer. And now it's easy to see that this is linear subspace. And the definition of our main object is like this. L2 of M is just the quotient linear space of L2 of M by L02 of M, and we also, using this manner, define the scalar product. So this is, it will be just the scalar product. So the elements of this will be denoted by classes. What does it mean? It means that this is the set of all G from L2 of M, which has the form G is equal F, or maybe just we can write it in a linear manner. Yes, we can just write that this is F plus L0 of M. Yes, we shift the zero layer by an element F. 0, 2, yes. Oh, this is like this, and because of this definition, this is just the property of the general construction, that dividing but such a subspace, so this is every time when we have a semi-norm, this is the linear subspace, not only in this case. Every time when this semi-norm comes from the semi-scalar product, we can define scalar product in such a space, in such a quotient space, and this is properly defined, and this is scalar product. So the definition is like this. We take just F and G, and it does not depend on the choice of F and G, of the representant. Yes? And the norm of F is, on the other hand, this is f class f to the power half, yes, this is m, and this is the same what yes, we have this. So in this way we obtained a linear space which is a scalar product case, and the main problem is it a Hilbert space or not? And fortunately it is, but to prove it is also not so easy. And I'm sorry, I have this proofs in my manuscript, and this is real manuscript, this is not typed, it's written by hand. I hope you can write this. And to fix many holes in the proofs you can find, there are several types of proofs that this is Hilbert space. To fix those holes, it was quite hard work to prove all the details. So I have done this, but it's a pity I don't have time to sketch this proof, but no, you should believe me that this is the Hilbert space and you can check it. I didn't make any mistake. Yes, but now, so this is a Hilbert space, and now I would like to say something about this subspace. It will be important to know something more about this when we obtain such a situation. I told you that this is not true. This is not so trivial as for usual A2 spaces. For usual A2 spaces, we could say the function is in zero level for usual measure when it's almost everywhere in the sense of this measure equal to zero. And here this is not true. So, I will...
I'm sorry, but...
We should finish.
Yes, soon. And I have to be in...
So,
at 3 o'clock.
Okay, so I will skip this part. You can read this, but this. Okay, I will write only the one condition. Yes, the condition. Okay, let f be in L2 of m. Then f is in L2 0 of m. If and only if f of t belongs to the kernel of dm of t for trace m almost each t belonging to. So this is the condition. So it's not important that we have the zero measure, but this is such a condition is important that the value, the vector, this vector belongs to the kernel of this, yes? But it can be not zero matrix. It's different. Okay, this is one thing. I have also an example when we can see the difference, but no time. And now, very shortly, about two subspaces, two important subspaces. One is the subspace of simple functions. So, simple functions. Functions, in fact, classes of functions. So, for typical L2 space, simple functions are the linear combinations of characteristic functions of a set. yes, of a set which has finite measure. Here we have in some sense finite measure, so each measure of set is okay, but the problem is that the characteristic function has real values, no real and complex value, but real 0 and 1, and we need functions which have values in CD. So how to obtain something which is similar? Of course, you should just take a fixed vector of CD and multiply it by a characteristic function. So, simple functions have the following form. We have a class of the linear space which are obtained like this. We take, no, not this direction. First, we should have a number, so we have a characteristic function which has real values, and we should multiply this by a fixed vector. So omega belongs to the sigma algebra and C belongs to CD. Yes, and we have the classes of all those functions, and we obtain something which I call S of n. Maybe this is better to write these classes here. Okay, so I take all those classes and I take the linear span of this, and I will call this the space of simple functions. And theorem is that this is always dense. The closure is equal to A2 of n. And the second important subspace is the subspace I started to tell you about. I will write it down very quickly. This is this space which was considered by some authors as the whole L2 space. So this is true for d equal 1, for instance, of course, but not for larger. It can be not true for larger dimensions. And let me find this. Okay. The subspace L2 sigma of M is the set of all classes of such F in L2, where F of course is in something I will denote by capital L sigma of M, and the capital L sigma F belongs to the not capital but calligraphic L sigma of M if and only if F is measurable and for n I equal from 1 to d, fj, this is just the jth coordinate, we can say, of f belongs to L2 with respect mjj. Recall I would like to recall you that this was the measure, the real measure, yes, the non-negative measure obtained from this. So, and it can be proved that for such two Fg, which belongs here, when we want to compute this semi-scalar product, Fg, we can do this just by this formula. J A. Alright, not to make any mistake. Okay. It's the sum of all the integrals like this. F, J, G, A. Yes. D, M, A, J. Oh. So this is true, and I told you that some people decided to define the L2 space by this formula and the scalar product by this formula. And this is true that for those such functions, all those integrals exist. These are integrals with respect to the not the non-negative measure, but complex measure. But it can be proved that this function is integral with respect to the variation of this measure, so it makes sense. Yes? But it can be proved that this contains the smaller subspace of simple functions, so this was dense, so this is also dense, and this is only the subspace of L2 of M, and in the case D equal 1 is always equal even, yes, but for other dimensions it can be equal but can be not equal, and when it's not equal by density it cannot be Hilbert space. And this starts to be a problem. Sometimes when we want to, for instance, use the formula for the scalar product, you sometimes cannot use this formula for scalar product. It simply can be not properly defined. This can be not integral function with respect to this. So we should be careful. Okay, so this is everything, and the next time I will start to speak about some more, I will start to reach our main theorem, yes?
Thank you very much. Any questions, comments? Also,
okay, so I am sorry that I was so late, but so what to do?